Now today is a brief summary of what we said yesterday about the three Ibrian, because I finally managed to get a better understanding, even though it's not easy, because I mean there is a lot of mathematical formalism there. So like I have problem myself in understanding, and if you want to understand properly, I think you should really go deep to like the mathematics behind. It's your own choice. I don't think it's that needed at this stage. So as you wish. Okay, so I share my screen. I share the desktop. So now we should all see the presentation. Uh, I added this slide to the third class of yesterday, so you will see it online. Okay, it's already uploaded, so don't worry about that. If you don't understand something today, you can still consult it. So as I say, today we go quickly through these different Ibrians. Then we go quickly on the different let's say the Python things that we need to see. And after that, we start checking your doubt about that. So the idea of all these Ibrians is to go to a local minimum of an energy landscape, okay? So you need to think that this is the space of all the position of your atom, in the sense that each point means is a given structure, okay? So the point here will be a structure with the atoms a bit different, this point here, same structure with the atoms still a bit different, so on and so on. And the idea is that the lowest energy configuration, so the is at the minimum. So like every optimization algorithm, both electronic or ionic, is done in order to make the point where you are, your initial state, fell into the minimum of your energy landscape. Okay? So we start usually very far away from the minimum, and we need through the algorithm to go here, and the minimum is with the color blue. Okay, I just point it out because then will be like useful later. So Ibrian 1, this full DIIS algorithm that yesterday I got a bit confused about. This is the one where you insert n3, okay? And n3 is the number of previous coordinates that you account for defining the minimum gradient. And now I explain this a bit better, okay? So how does this algorithm work? You give a potting. The potting would be the step size. This is the size view, okay? So you need to think that this like is the top view. The minimum is where the blue is. The minimum would be here. And this side view is like if you are taking these systems and you are seeing it from the side. So now we are on the top, think that you are from the side, so you want to go to the minimum, okay? So the potting is your step size, and since you don't know if the step size that you give is larger or lower than the position of your minimum, so your optimized like position that lower the energy, at least globally, what does this algorithm does? So you start from x0, so you start from this position, let's say, you do a step, so you optimize your position moving along the gradient. So the gradient here is g0, okay? And you go to the point x1. The point is that the point x1 is not sure that is the minimum. You know, you don't know. You just went to the direction, and you know that x1 is in a position of energy that is lower than x0. So for instance, here you go from this point to this point. It's true that this point has a lower energy than this point, but this is the minimum. X1 is not the minimum, and instead you want to go to the minimum. So how do you do? In x1, you calculate the second gradient. So this g1 is the other gradient. And then you look for linear combination of the coordinates x0 and x1. What does it mean that you look for like the linear combination? If you want to get the idea, just simply means that you look for all these coordinates, okay? Your algorithm looks for all these coordinates and select one coordinate that minimize the gradient, okay? So x0, you move to x1, then you take linear combination of x1 and x0, you go to see all the coordinates in this area, and you calculate the gradients for all these coordinates, okay? And then you say, look, x1 opt is the one that minimizes my gradient. So it's a good point because actually it's the one, is the local minimum, okay? And then from here, you calculate also the gradient in one direction, and then you move along the gradient, and then you repeat this process for all the steps. What is n3? n3 is the number of coordinates that you are keeping in history in order to apply this algorithm. So in this case, n3 is basically 1, let's say, because from here you're just keeping one position. But think that you are like after n step, if you put n3 equal to 10, means that this linear combination of coordinates will account for position 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So more n3 you give, more knowledge you give to the algorithm, where like of different position, of different space of position. So like better information you give, where is the coordinate that minimize the gradient, okay? So it's, I understand that it's not clear. I mean, it's not that it's not clear. I mean, it's rather complex. But what is important for you to know that this algorithm kind of keep the idea of the previous steps, the knowledge that it got from the previous steps, and it applied to look for the minimum gradient. So that's the reason why this algorithm is very good if you are already close to the local minimum. Because if you are here, it's good because let's say you will have all the direction or the gradient that they are pointing more or less here. If you try, for instance, to apply this algorithm here, it may fail a lot because let's say that, for instance, like you get all the points, all your or your space of coordinate that you are checking. Think if you get all of them in this line that is really far away from the local minimum. So what will happen is simply that like you will keep moving along this line and you will not see the local minimum because all the gradients will be along this direction, okay? So this script is really, well, this algorithm is really good if you are close by to the minimum, because then you keep all the information that you already got like previously and you can just fill inside the local minimum, okay? Try to read it again, check the answer. This want to be just well, not a suggestion, but a help to understand, because as I said, it's very complex, okay? But what is important here is that apart from the plotting, that is the step size, so basically this distance, okay? You also take n3 because n3 is the number of previous coordinates that you are keeping in your algorithm in order to check this, like in the space of coordinates, what is the given coordinate, the given position, the given crystal structure that minimize the local gradient. And then you go to the point and this is x1 optimum, okay? And then here you calculate the gradient and then you apply also here the same approach. So you move to x2, then in x2 you calculate g2, then you take the linear combination of x2 and x1, you have a space here, you calculate like the coordinate that minimize the second gradient and so on and so on, okay? And for instance, if you have n3 equal to 3, we can go to x2, x1, and x0. So we keep also x0 in the iteration, okay? Second one, and maybe it's easier to see also the difference. Here, conjugate gradient algorithm, Ebrion 2. Here, the plotting is the initial step size. So basically, when you move from x0 to x1, then what you do, you take an interpolation of the different energies across this, let's say, this step. So here, these are like the point that you calculate, assuming that you have like a quadratic fit or like a cubic fit. And then what you get, you calculate, you estimate the energy for all the points, and then you can get the minimum. So let's say from your initial step size, you would have gone from x0 to x1, but actually thanks to this interpolation, so these 4 points are the 4 points that you are here, at the end you see that the real minimum or the real local minimum is this one, okay? Then at this point, you move along the gradient S, and S is defined by taking the conjugation of gradient 1, that is the gradient calculated in the position x1, and the gradient 0, okay? So by default, in this equilibrium 2, you are keeping n3 equal to 1. So you don't put n3 because n3 for equilibrium equal to 2 is equal to 1. And why n3 is equal to 1? Because here you just keep one step in your history. So here you just always keep the information from the previous step. In this case, x0. Let's say if you then move from x1 to x2, with equilibrium 2, you just keep the information of x1. You forget about x0. And instead, in equilibrium 1, we said before that if you put like n3 equal to 3, you can still keep the information about x0 step. So the main two difference is that here we apply an interpolation to go to the minimum. Here we don't apply any interpolation. We just go to the space of coordinates and we check which is the coordinate that minimize the gradient. Here we always just consider the previous step. So x1 we consider x0, while here we consider all the previous steps that we want until we want, okay? So if we put n3 equal to 20, means that we are keeping in the history all the information about the coordinates of the previous 20 steps, while here we don't. Here we just keep the previous one. And then here we get the linear combination of the coordinates. So whenever we are talking about linear combination, you need to think it's simply like to sum the two coordinates, okay, with two parameters. These two parameters need to be normalized to 1. And instead here you apply another mathematical like function, that is the conjugation, okay, that you can read online. What it is rather complex. But let's say the important point is just that here you keep information about all the steps that you want, here you don't. So in this case, if you are really far away from the minimum, the fact that you are keeping so much information may give you a lot of problems, okay? Because, yeah, like maybe I can make a quick draft. So let's see. As always, okay, annotate, come on, yes. So let's assume now that we are here, okay? Let's assume that we are here. And let's assume that we are keeping all the information. So now probably you have something like that, okay? If you keep all of these, so if you keep all the information from this previous gradient, like maybe your space of coordinate, well, your linear combinations, so basically like where you want to go, goes to this direction. So instead of going directly to the minimum, goes here, because it's still keeping a lot of information about steps that were not that important, because these steps are really far away from the minimum. Okay, so that's the reason why this equilibrium 1 works very well if you are here, because then, you know, like the information that you get will, I mean, all the coordinates, all the gradient will just point toward the global minimum, toward the minimum where you want to go. While in the case of equilibrium 2, since you get, let's say, an interpolation, this is much more robust and solid. The problem is that, of course, since you apply an interpolation, can also take a bit more time. So that's the reason why equilibrium 2 usually is the more stable one. Equilibrium 1, if you are close to the minimum, will just like push you to the minimum much faster. And the very last one is the one that we introduced yesterday that you will not use much, that is the damped molecular dynamics, so equilibrium 3. Here you define like potting and S mass. So this is easier because this is just applying the law of dynamics to your point, okay? So you have like a force, you have like a speed, you have an acceleration. So this is your potting. So let's say that whenever like you apply a potting is the time step. So basically tell you how much you are advancing, okay? And then every time you finish a time step, you again calculate the forces in this point and you follow the forces, okay? And as I said, since we apply a friction that is applied with S mass, then the important on S mass is that if you put a S mass that is too high, then you will stop before your minimum. If you put a friction that is too low, then you will just go beyond your minimum, okay? So you need to think whatever process that is, okay, yeah, like we can, like if we make an example, with the friction on a table, for instance, like if you assume to have a bottle on a table, something like this, so what will happen is that depending on the friction that your table has, like, and depending on the forces that you give as well, what can happen is that if you push it too much, well, too slow, then it will stop before getting to the border of the table. And instead, if you don't put that much friction, so let's say if your table is very, very, very flat, then it can be like too fast and then it can go beyond your minimum, okay? So in this case, in this graph, that means that like as mass too low, this case, you go up, so you stop here, that is not your minimum, so that's wrong. But if it's too high, then you just stop here. So you're not, again, you're having a bad estimation of your minimum because your real minimum is here, okay? So check this slide, check all the formalism in the Anson tree, because there you have a bit more word. This is just again like to give you a flavor about what is happening in a bit more, hopefully, simple way. And don't spend too much time about that. I mean, like the important point to remember is that Ebrion 1 is better if you're close to the local minimum. Ebrion 2 is more stable anyway. Ebrion 3, you will not use it much, okay? And you will always get the input, yes.
And smash, and so how could we set it? Because it will not be too big a value or too small
Well,
value.
whenever you don't know how to set something, you make tests.
Okay.
So you can make tests. You can have a benchmark system that maybe you calculate with Ebrion 2, and then you calculate with Ebrion 3 as well, so that you see that you go to the same minimum. So you can do some benchmark tests. Or usually somebody else is telling you. Let's say somebody else did this benchmark test before you, and then can tell you, look, Sichen, this is the best value because I already tried. Okay? Good. So I hope this at least doesn't give you more problems. I know it's complicated, so don't worry about that. Then I'll go very quickly, as promised, about write the script, and then we can start discussing about the answer. Okay? So this is the script that Sichen and Rick need to do. So the one that we were, okay, we are already inside. So just to discuss a bit the structure, okay? Okay, now it's a bit too big, I think. Okay, so, well, at the beginning you always say what you're doing, okay? The script takes the concar and insert a molecule on top of one of the surface atoms. Then it's telling you how you need to run the script. So you need to run the script plus add a number, label of the active site where you want to assert the molecule. Label just means the number, okay? So if in your postcard you have all the atoms, so the 12th atom may be the surface atoms where you want to put the thing. So there you will put 12. If that atom instead is 15, then you put 15. If that atom is 3, you put 3. Okay? This is something that the user of the script will have to put. But that, I mean, makes sense. Then, this command that maybe some of you, I mean, that you have seen also in other live script, this is just to give you the permission to execute. Because usually all the other file, like you see here that there is a difference. This is green, this is white. And the difference is that here you have the right to execute it because this is a script. And here instead you just have, in this concar mode input, you just have the right to write and read it because this is a file. So on a script, you need the right to execute because you execute a script, the other one a write, okay? And that's the reason why, in order to change permission, you need to use this chmod plus x. So plus x means plus execute. So it's telling you, give me the permission to execute. Input, $1. Whenever you put input in bash, you always put this, okay? $1. You can also avoid this line because it's commented, but this is just to remind you that whenever you would like to read this number, this n, you need like to put this as a variable written as $1. Okay? If you put $2, means that your script will read whatever number as the second variable. $3, 3 variable, okay? So that means that, for instance, in this case, you see, okay, yeah, this is, more. Yes, you see that, yeah, because this is really, yeah, this was really general, the script, okay? But like, for instance, here we are calling a variable that is var1 $I, and in case, for instance, you wanted to call this variable, you would have needed to put $1, okay? So just to go, I know and I'm aware that it's really simplistic, the structure, but because you already have all the tools in the previous two scripts. So here you need to think a bit more by yourself. So let's say, remember that whenever you do a script, the important part is always to understand what is the things that you want to do in a manual way. So now you have to conquer. What you want to do is to take two coordinates from one concar that are the coordinates for the CO, move it inside the other concar. So you will need to add these two coordinates at the end of the previous concar, at the end of the concar of the structure. And then if you have done it, you will need also to adjust the number of elements and atoms on top of your concar. So maybe it's better if I just open the concar because then it will be easier. Okay. So let's take the concar of your surface. If you want to have this CO on top, you will have to adjust this line. So you will have to have it also C and O, carbon and oxygen. You will have to put here 1 and 1 in the case of carbon and oxygen. In the case of another molecule, you will need to put something. This information you need to read and take them from the second concar, okay? And then you will need to append the coordinate of the CO at the end of the script. So you will need to add two lines with the coordinate of carbon and oxygen, okay? What is the problem? Is that if you just do it in a very simple way, so now let's take the concar for your molecule. So like you need to find a way in the script to copy these two lines and paste them here, CO. Then you need to copy these two, 1, 1, and paste them here, okay? Then you need to take these are the coordinates of the CO, and the very simple approach that you need to do at the very beginning will just be to be able to copy this one at the end of this concar, and then you are done for the very draft 0. Of course, the script will not work because the script now will put this carbon and oxygen in the Z position 6 and 7. So that will be in the bulk. That will be like bad because you will need to adjust for X, Y, and Z position, but at least you are very close by. Because then the last step of the script will be to take these two coordinates, okay, and then you need to make some summation in order to have this coordinate in a position so that they are, so that your coordinate, your CO is on top of one of these atoms. Okay, so let's say if this is the atoms where you want to put it, then you will need to do that. Instead of 7.5, you need to have like 8.25. Instead of 7.5 here, you need to have 10.20. And instead of 6.26, you need to have here something like 8.26, because we said yesterday it's good to have two Armstrong like space. And here instead you have something like, you need to take this difference basically, because you also need to preserve the distance that you have between the carbon and the oxygen in your system, okay? So given this introduction, that is always the most important one, because remember, whenever you do a script, you need to understand what is the structure of your script before. You need to understand before what manually you need to do. And then you implement it as a script, but because otherwise you get lost, okay? So taking that into account, then it's telling you, okay, you need to derive from the two concar how many elements and atoms you have in the system, okay? So you need to know how many you have in one concar, how many you have in the second concar, and how many atoms. Later, you will have to adjust the line of the elements and number of atoms so that you are probably accounting for the inserted molecule. And that is what I meant. This is your preliminary concard where you just have indium palladium, but now you also want to insert carbon monoxide, so CO11, okay? Then here is giving you a hint how to adjust this value, okay? You can use this utility, and this utility like allow you to add either a symbol or a number in a given line. And you already use it in the script where in the first script you did. You use this command. You may have not understood that, but you use it. So you need to go back to that command, understood how you use it, and then you implement also here. Okay. Then this command help you to take X, Y, Z of the molecule. So for instance, of carbon monoxide. So if you play a bit with this command, okay, what you can do is basically to have like 6 numbers. So like carbon X, carbon Y, carbon Z, oxygen X, oxygen Y, oxygen Z. And then from that, you use the BC utility to sum the three coordinates with the ones of the active site. Okay? And here you have the way to calculate.
But you
Yeah.
have to sum the coordinate x and coordinate I of the active site with the coordinate of the molecule, because if you are placing them, you have to just substitute,
Exactly.
but not sum it.
I mean, I say sum it in general, like in
Okay.
view of this algebraical sum, but yeah,
Okay.
you need to substitute.
Okay.
Okay? Because you know, like the other approach, the other approach you could do if you want to make it easy is just to take this, you move this to 0, 0, 0, 0. So let's say you subtract in this concave like the 7.5, and then in that point you just need to sum it. Okay, so that's what I meant, because I remember when I did the script myself, that was the easiest approach I had. But indeed, the other approach can just be to substitute. Okay, the problem with substitution will just be that, remember, like in this case is good because you want to put the carbon on top. You are taking a really special molecule where you see that the position of the carbon and the position of the oxygen, the X and Y are the same. But remember that there may be molecules where this doesn't work, where here you have like 7.4 and 7.4. So the substitution will work for your atom 1, because your atom 1 you want to put it on top, so works. But for the second one, it always makes more sense to sum it, okay? Or to subtract, depending on the thing.
But it could happen that the second atom is at 7.4. I mean, it would be if we place the first atom at 0, 0, 0, the second one would be outside the box.
Yes.
Right?
Yes.
Okay.
But this is just because you are translating your first atom
Yes.
to the 0 coordinate. I mean,
Yes.
it's your choice.
I mean, in this case, maybe it will be maybe it's little, how to say that, little easier than the other, because just there is a molecule, small molecule, CO. I mean, in the case if we have a big molecule, just like a little bit, just like CO2, there is an angle between the two oxygen and the carbon, and maybe there is more complicated, just like CH4, or even more complicated. So the case will become, I don't know if we can program that.
The point is that there is no complexity, let's say, because all the information of angles are stored in the structural information. Okay, so if you have the concard of the molecule, you have all the information that you want. And if you make this concard work for CO, I can tell you that will work for every molecule. Because like whenever you get to have this molecule, this concard of the second molecule with like one center, one of the atom to 0, 0, then it's just you are translating the whole molecule to 0, 0, and then you will just have to sum the coordinate of this molecule on top of the second atom. But remember that for that, in the script, you will use a 4 cycle. So like if you have like 20 atoms in the molecule, or 2 atoms, if you program your script accordingly, there will be no further complexity. Because the angle that you mentioned, the information about the angle is the information that you have in the structure, in the distances, in X, Y, Z. Okay?
Okay. Okay.
So, just to make it a bit easier to understand. What the script will need, so you need to do two things, okay? You need to, let's say, okay, let's do it easier. So, first things that you can do if you want, you do it manually. Okay, now I need to open this. Well, actually, I can just copy the things and I do it locally here. That would be easier. Then I open a new terminal and I do like one. Two. And this one will be confer more. Okay. Okay, so remember that whenever, and now I make it larger, whenever you like run a script or make a script, the first approach is just to make sure that you're able to run the same script locally. So locally means okay. Why? Okay, okay, well, we will do it here. So what you want to do, what you want to do in the script is to copy these two lines. You copy them, okay. Then let's say you will have concar one. Now I'm doing it with Python for VASP because I'm doing it manually, but you will need to find a way to do it automatically, okay? So if I do this, okay, there is something missing here. Why did I save? Okay, so retrieve it again. Probably didn't save before. Okay. Okay, let's okay. So you have this. Okay. So this is what you want. This is what you have. Then you need to put the CO molecule on top. So what you do it like manually, but we don't want to do it manually because otherwise if you have more than like two systems, you will get crazy. You copy this, you copy, you go to build, you go to text, you append it to the end, you go up, you adjust this line, you put CO, you put 1, 1. So this is the first iteration of your script. The result of your script will be this. Will be like just to copy the coordinate and to put it inside the cell. Then the second part of the script will need to do some things so that you can move this atom on top, for instance, of this atom. So you, in this case, it's easier because you go to edit, move atom, get, move from the first to the last. You don't want to move the last one. And then you are like the 2 angstrom of offset. And then you move. Okay. But if you think about what we did, I mean, it's rather simple because what we did is just to add CO here, 1, 1 here, to add the 2 coordinates that we had here. And then we make some mathematical operation so that the XY coordinate of this carbon are the same of this atom number 45. That will be the active site where you want to put the CO. And then on the Z you have something in order to have it with 2 angstrom offset. Okay. So this is very easy to do on a Python for VASP. So it should be also easy to do it in the script. Like this, the concept is easy. The implementation may take time, but the concept is easy. Okay.
What was the command to move the molecular from
Edit, move atom, then you get the group. Then you get, for instance, these and these. Then you can move like from the atom 45 till, so you get like move from the first atom, that is the 45, till the last one, that is the oxygen, and then you move and you can adapt here the X, Y, and Z. But this is not the I mean, this is nice that you have Python for VASP to do it, but you need to find a way to do it automatically. Because as I say, now it's okay, because I need to run one system. For a project, I needed to run like 500 systems, and I cannot put manually 500 atom on top of another, because otherwise I will get crazy probably at the end of the day. So you need to find a script that does it for you. Okay? And you can try. I mean, like, it's not impossible, and you have all the information in the previous script that you have. You just need to read it a bit more. Okay. So I think that for all this introduction is already a lot. Doubt about the answer, in case there are.
I have a few of them, but if someone else wants to start, because I always start and I feel guilty.
Maybe
not I can start.
Mariam, do you want to say something? Do you manage to run the first one? No. Wait. Yeah, talk. Yeah, go. talk, Mariam. Go ahead. No, but we don't listen.
Yeah,
Wait a second. Okay, sound setting.
Really?
Sound now. Okay, doesn't matter. Try now. Yeah, talk.
And the script.
Can you listen to us?
no, creo que es su problema.
No, I think it's our problem. Let's see. Here is Zoom. Yeah, wait.
¿Podemos cerrar y abrirlo otra vez?
No. I mean, if we open and close Zoom, wait. Okay, I just need to see. Oh, this setting. But I mean, we. Okay, now yes.
Is it okay?
Yes.
Yep. Okay.
Yeah.
No, actually, I even didn't have any idea how to start the process and this kind of thing. So today, Santiago, thanks to him, really helped me. But I think that I need to work more about it because, I'm in a really, really basic steps. So I need to work a lot, I think.
Yeah, I mean, take your time. Like, don't rush, because you need to learn the concept and make sense, because like you're like just now. The only important point, and maybe you can try before then we close the things, just try to run one single system, because what is important is that to prove that you can run and submit a system properly. Okay, so like,
okay,
because that is the most important part, because that may be a technical issue, and if you have a technical issue, so you may get stuck for like days again, so like, maybe now when we keep talking about the other DAP, just try to see if you can submit and run like the simulation that we said before. Remember that in order to submit, when you are in the supercomputer, so let's say I can just enter your own like folder. I mean, I will, this one, yeah. So let's say if, okay, yeah, this is answer 3, perfect. So let's say here, okay, but now, let's see if you manage. No, now you manage.
Yeah, that's right. Today with Santiago, you helped me.
Yeah, no, I know. But the point is that at least now, or let's say, at least the procedure works. So now, of course, you need time to remember the procedure, to apply the procedure yourself. But the important point is that the procedure works. Because if the procedure doesn't work on your computer, then you can learn a lot, but it doesn't work. So the important point is that it works. that you have like one system that works. So you have one postcard that works, you have a structure that works. So keep this folder as an idea, okay? So that if the
Okay.
next one fails, then you can go back here and say, okay, look, what is the difference? The difference that here I don't have this parameter, then you're done, okay? But that is
Okay.
so like take your time, and if you have questions like this afternoon, Monday, Tuesday, whenever, just send email to me, Santiago, the others, no problem, okay?
Thank you very much.
Don't worry, take your time. Good, then, who's next?
Yes, question about the question
Yes.
yesterday, and here I have a problem between the in the 3-2 just to calculate the density of state,
Which problem do you have?
and in the in-car, and I compare it to the other one, the 3-7, just to absorption of a CO molecular over the nickel 111 phase, and to calculate is the density of states. And here I don't know why in the first one, the 3-2, they have taken in count the I spin 2 and the maximum 5 one product, but in the other one they didn't think anything about that. But I mean, we are work with the same surface. Why in the other one we didn't? The thing did not take account.
Good point.
And also, I don't understand well the ruins. I have read the wiki WASP, but I don't understand why we should do that.
Okay, so over the spin is simply a mistake of the Anson, in the sense that I told you, like the Anson doesn't make, so all these Anson are not made to make you have the best calculation ever. It's made to make you try all the different times. So they apply the spin for the nickel alone, because on nickel, since it's magnetic, you need the spin. And then they forgot to apply it on like this LDOS, because in that case, they were not interested in having spin. But indeed, if you have nickel, whether you have the adsorbate or you don't have the adsorbate, you need to keep the spin, okay? So for instance, that's the reason why if you take the 6, you see that the 6, 3, 6, nickel 1, 1 clean, this doesn't have the spin either. You see that here you don't have the spin in the 3, 6.
No, I also did not understand why they do this.
But why they don't have the spin? Because like what is important in VASP is that if you want to calculate absorption energy, you take the same setup. So what will be wrong is to put the spin on nickel and not to put it on nickel plus CO. In this case, both your clean nickel of reference and nickel plus CO, they don't have spin. So the difference of energy between the two will not be correct as to repeat the same study with both the spin, but will not be too wrong because you're still assuming that there is no spin for both the systems. So in general, for nickel, you need to put the spin, but as I said, Anson, they just want to try things for you. They don't want, I mean, they are not the perfect exercises. So they don't put the spin because it's a mistake. Easy thing to do, okay?
And in fact, it only puts the spin in the 100 surface.
Exactly.
The other surface, the 111 surface, are without a spin.
And then let's go quickly on these air wings.
Yeah, this I don't understand well what is it, because podium means the site in, I mean the distance for every
But I mean, like you have a so here like the definition is easy.
Yeah.
Wigner states radius, so you need to see what is the Wigner states radius, and the Wigner state radius is the radius of a sphere whose volume is equal to the mean volume per atoms in a solid. So you have the explanation. I mean, like this is the parameter that you put, okay? then like you can ask me, but why do we need to put it? Okay.
Yeah.
And then like what he's telling you, like as far as I understand, yeah, like so this is just to have the electronic convergence more or less, okay? In the sense that you are like you are giving extra parameter to your simulation, defining what should be this radius, so that if you define the radius, they should have a better idea of where the electron should be, let's say. But it's not a parameter that is straightforward. Like I never use it again in my life. Okay. So that is just the point. Like, as I say, like it's important to learn all the well, all the different like tags, but don't focus too much. Like what is important to know what it is and to read to understand a bit. But then like sometimes a lot of tags you just apply them if it's needed and you will get, I mean somebody will tell you. And as I say, this tag I never use it in my life. Okay?
And the other one is LVTOT, true. And then like I remember in the other case, in the 3.8 or 3.7, I think 3.8, no 3.7. There is another case. They also use this with I edible, L people, and I don't know why use this in this case because dipolo means they are talking about taking account the dipolo with in the cell and next no because there's another because in the other case they didn't take into account this.
Okay, so again. So LD thought, just write a new file that is called log thought, where you store the local potential. Okay. So where you store the electrostatic potential that you have in the system. So this is L thought true what it does. If you put it false, you don't have log thought. If you put it true, you have log thought. Okay? This is the easy solution. Then what you just said about the dipole is correct. Again, don't focus too much why they apply or why not. I mean, just focus on the tag itself. So you copy it, L dipole, and you see why. So you click on that, you open this, okay, and it's telling you switch on correction to the potential enforcement VASP. Can be applied for charged molecule and molecules slug with a net dipole moment. As you say, they apply it on CO because CO as a dipole is true. But on top of that, in principle, you should apply it whenever you have a surface. Why? Because the problem for the surface, and let's see if I can open the con card, if I have it here. Okay, now. No, not con card one. So the problem is that you need to remember that all these systems are periodic. So what it means that all these systems are periodic means that this is your cell, and this cell will be repeated like infinite times in all the directions. Okay? As well on the z direction. So intrinsically here you already have a dipole. Intrinsically. Okay? Because here you have a surface and here you have another surface. So let's say, for instance, you may have some electronic density here, and if you have an electronic density here, on the bulk you will have less electronic density. Because if you have more electronic density on the top, then on the bottom you need to lack some electronic density, because this is like a metal or a semiconductor. And you are not adding electronic density. So that means that here will be plus, here will be minus. And here you will see the plus, here you will see the minus. So here you have a dipole as well. So the reason why you always need to insert a dipole moment in the z direction, that is this one, is because since you're using an asymmetric slab, and it's asymmetric because you're just relaxing on one side and in the other side is fixed, is a bulk, okay? So you have a different electronic structure depending on if you are on their surface or if you are in the bulk. Then you are creating an intrinsic like dipole moment in the system that you need to correct with that thing that we just said. Okay, so just to clarify, this may be minus, this will be plus, this minus, this plus.
Yeah.
So you have a dipole moment here, and then since you have a dipole moment that is repeated infinitely, then you need to correct it, and you correct it with E dipole. And E, well, I mean, now I'm not writing, but still. And the important point, drawing, and the important point is this one. So now if I close this, you see L dipole true, that means, okay, you will use this dipole, and I dipole 3 means that you go in the other direction.
I mean, the correct it means eliminate the
What?
correct. You have just said the correct the dipole the develop
See, you correct for the dipole, yes.
yeah, but
Because you want to remove the dipole because the dipole is an artificial dipole.
And what the correct means that
To correct means that you have an artificial dipole in your system that is just given because you are artificially assuming a periodic boundary condition that is not in the real system.
Yeah.
So to correct, we just need that you apply on your system a value of the dipole that is the opposite, so that you have, let's say, a positive dipole in that direction. You put a negative one that you add. So the reason, like whenever you put L dipole true, means that you are applying a opposite dipole in your system, so that the overall dipole is 0 and is the dipole that you should have in a system. Okay. So to correct, I mean, in DFT, to correct something always means to try to avoid artificial mistakes that are intrinsic to the methodology. Okay. So here the problem is that with periodic boundary condition, intrinsically we have the problem that we have an artificial dipole that is not real, it's just there because we have periodic boundary condition, and so we need to apply a dipole in the other direction so that they neglect each other, and so we don't have any overall dipole. Good. So Santiago, Enrique, who goes?
Yeah,
I have no doubt.
Okay, I just have a few of them. I think that they have a quick response. And the first one, if you could bring the difference between the Postcar and Concar of 3.1.
Okay.
Because I don't know if it's my fault, but
wait, but I need to go to my.
Yes, because what I found is that some positions that must be fixed are changing.
Okay. Okay, so Postcar.
Okay.
Okay, so these are the difference. Okay, so this is your Postcar.
Yes.
And this is your Concar.
Yes, and the three first atoms should be fixed because must be fixed because we have those three Fs.
Yeah.
But when you see the Concar, you see that they have been moving. Which is the reason?
Yeah, the reason is just like the intrinsic like mistakes in how can I say, like number optimization of VASP. In the sense that like this, you see like so the difference here, I mean, like in general there is no big difference because remember this is like Cartesian and this is direct. So the difference between like you have like 0.5 and 0.1, like the big difference is just given because you change like from Cartesian to direct. There is still a difference, as you mentioned, that is this 14 and 28 that shouldn't be here. Here should be 0, 0 and 0, 0. And the reason for that is just because like when it does the revision, VASP kind of keep the good result till this, okay? And then here it just approximate badly. So the reason why you see this 14 and 28 here is just because like when VASP, let's say multiply this 0.5 by 350, well, actually divide this 0.5 by 3.53, then at one point you just say, okay, I don't mind about the extra like numbers, digits, and then it makes a mistake. So these are mistakes of VASP, but they don't move in principle.
WASP, the software, understand Germany?
No, I mean because that was done in Austria.
Yeah,
So VASP is originally from Austria, and they just understand. So whatever you put here that start with C or K, for them is Cartesian.
Okay.
Oh, okay.
Okay,
You can put just a K, for example. Okay.
exactly.
Okay. After that, I wanted to ask for the. I think it's in the. Yes, when we are changing the in-car of 3.3 using the CHE car output of 3.1. As I understand, those values that we are copying are the grid points that, or the grid divisions that the system has been generating. But which is the reason that we choose in, for example, this is, I think that, yes, this is a simulation that we run in order to see better the band gaps, the band diagram, which is the why we are specifying that on the in-car.
Yeah. Okay. So the point is that there is no reason, in the sense that like here, the reason why you want to adapt this line to the number that, as you said, you take from the changing car is simply because in the previous simulation, you didn't set any parameters. So by default, VASP assumed those parameters. And now what is important, so you can also try, for instance, to run like the same simulation, and instead of putting this 144, put 143. And the simulation will fail, because these parameters simply help VASP to read properly this CHG card, because this CHG card is taken from the 3.1, and here is telling you, if you check online about how the CHG card is like given, here is just telling, this is just basically the postcard, okay, you just copy the postcard, and then it tells you like the division of the grid. So this is the discretization in the X direction, Y direction, and Z direction, and here there are like all the points of the charge density, okay? But what is important is that since in the previous calculation, we assume this value because VASP decided, now we need to keep the same value here, because if we don't keep the same value in this in-car, then the simulation will fail.
Because it cannot read as an input the CHG.
Because it will try to read this as an input, but then it will be like, but look, I mean, like you give me much more discretization than in the than the input, the real input, so it's wrong. Okay.
So it's just fixing some of density calculations from another simulation.
Exactly. But in principle, let's say if you wanted to run the system better, you may have put this value in the 3.1, increasing them. So if in the 3.1 you put this line and you put like 50, 50, 288, then you get more discretization, and in principle, all your electronic properties will be better, but it will also take more time.
Yes. But if you want to put
because you get more discrete, you know, like, I mean, for any modeling, whenever you like increase the discretization, you get better accuracy, because, you know, like you have, let's say, instead of having like a view over like 1 angstrom, maybe you are discretizing by 0.5 angstrom, so you have a better definition of how like locally the electronic density is changing.
Yeah, but maybe you reach a point that that improvement is not meaningful, and
Exactly.
just wasting more time. Okay, but if we wanted to improve the first simulation, we could copy those parameters, increase them, but also we don't have to include a CHG card in the
No, because here you are generating. So the reason why you need like to put this parameter in the T3 is because look at the first line. Here you are telling them, look, read the CHG card. And instead in the 3.1 there is not this line, because in this card you just take E charge equal to 2. That means that you are assuming that to optimize the electronic density, you are just taking the superposition, the overlap of the atomic orbital.
Yes. Okay. Okay, I wanted to ask also, when you are trying to calculate the desorption energy of the CO molecule in the surface.
Mm-hmm.
It tells you about to compare it with experimental results. And seeking for experimental results, what I've seen is they are classified, or there are different results depending on two concepts that are the coverage and the exposure. And I understood coverage is like how many active sites are considered to be absorbing the molecule. But I have not understood what exposure means. But anyways, how we can know those parameters in our simulation?
Yeah, that's a very good question. So okay, let's see. So the exposure, I need to check. I can tell you money because I'm not that familiar about the term, and I'm not even sure that
it's something related with the CO molecule, but I have not written anymore.
About the coverage, let's say the answer is rather easy because we have a way to simulate the coverage. Well, simulate to get an idea about how much the coverage is.
But being our simulation with periodic boundaries, it will always have the same coverage, right?
No. Yeah, I mean, it depends on how much. Now I will show you. You will get clear. So this is your system, right? Okay. So as you say, since it's periodic boundary, I mean, it doesn't matter if we multiply it by 10,000 or not, but you will still have the same like coverage. So the coverage in this case is one. One in the sense that it's like one atom, one monolayer is called, because like it's simply like that you have one CO for every like nickel that is on top. So the coverage here is one, okay? That is the maximum coverage. You will never get to this coverage. Like for nickel, usually like 0.8, 0.9. If you want to study a different coverage, what you could do, for instance, is to remove some of the CO. So how do you remove some of the CO? You will need to take a bigger slab. So for instance, we can multiply the slab 3 per 3. So now we have a bigger crystalline structure in general. And then what you can do, you remove some of them. So for instance, now if you want, you can remove like you remove all of them apart from one.
The one in the center, yes.
Exactly. And now, okay, I always forgot that to do that. I need to go to build. And now if you go to remove, okay. So now you have 3 per 3. So now you have 9 nickel atoms on the surface. You see this nice 3, 6, 9, and you have just one CO. So now you are studying the coverage of 0.33 monolayer. Okay, so that is the way that you can study different coverages with DFT. And indeed, depending on the coverages, let's say, if you try, for instance, to calculate the absorption energy of this CO and the absorption energy of the previous CO, you will see that the absorption energy of this CO will be much higher than the previous one. Because in this system, so in the previous system, I need to click on reload. No. Yes. In this system, there is very high coverage. So that means that there is a lot of repulsion between the CO molecules because they are really close by. So there is repulsion. That means that the absorption energy will be lower, like the CO may dissolve at some point. But if you have a very low coverage, then no, you don't have any repulsion, so you have the interaction that is as strong as possible.
So you told me that the disruption energy on the lower coverage, sorry, the lower coverage, yes, would be higher because it's more difficult to dissolve it.
In the low, you mean? Yes. Yeah, like
low coverage.
Okay. Exactly. Like so, absorption and desorption, they are the same, just with a minus in front. So what is important is that if you have low coverage, you have a stronger binding. If you have high coverage, you have a lower binding. So that means that your CO can dissolve simply because you have a lot of repulsion between neighboring.
Yes, understand.
Okay.
Okay, thank you. And the last question for me is, I think that the simulation 3.7, I think that the idea of that simulation is to use it in order to see the interactions of orbitals, because you told the last class. But could you explain a little bit about this, because I did not understand. I understand how you printed different lines on the density of the states depending on each atom and each orbital, but I did not understand how you analyze the interactions when those lines are crossing.
Yeah, I mean, yeah, because let's say the way that you analyze it from here, it's really, really qualitative. So that's why you didn't properly get, because it was also very qualitative my explanation. So what is important? Okay, what is important for you to know is that, like, whenever you have an interaction, you need to have an overlap between different bands. Okay, so the way that, like, let's say I was defining the things is that, for instance, if you have nickel, okay, let's take nickel, let's take... Ah, tenéis ya cita, ¿no? Vale. Sí, 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 no, aquí hemos alargado 5 minutos, pero vamos ya. Perfecto, gracias. Sí, 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 no, que estamos acabando, la verdad. Mariam, we need to leave. Sí, 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 sí. Gracias, lo siento.
Okay, thank you very much, Federico.
Sí, sí,
Comentamos abajo, pues, ¿no?
sí.